Okay, this podcast takes you through the answers to quiz 2. That's the quiz that you got in the second week of the course. Most of the questions just checked that you'd done some of the reading, but some of them also covered statistical concepts. The first sentence of George Orwell's 1984 was "The clock struck 13." An interesting novel because it makes a lot of the use of numbers in modern society. An important influence in the early development of statistical thinking, you were given the options of agriculture, astronomy, warfare, navigation, and so on. They were all important influences. The point is that statistics grew out of its practical applications. It wasn't just a kind of intellectual pursuit. The doctor who discovered that contaminated water spread cholera and did so by collecting data to get evidence, which is the essence of statistics, was John Snow. I suggest the key concepts of statistics are measurement, variation, uncertainty, correlation, and models. The three levels of measurement that variables can take are nominal. That's when you have a categorical variable where you can just put things into different categories, but you can't really say anything about the relationship between categories. An example of a nominal level of measurement might be the classification of somebody's religion. You can say that they're of different religions or perhaps of no religion at all, but you can't really say anything about the relationships between those religions. One isn't bigger or smaller than the other. Ordinal are where you can put the categories in some kind of order, but you can't say anything about the distance between them. You can't specify arithmetical relationships between them. An example of that might be social class. You can put classes in order from working class, middle class, upper class, or something like that. But you can't say that upper class is twice as big as middle class or something of that nature. The final level of measurement is interval, where you can make directly quantifiable statements about the values of a variable. So if you measured somebody's height and one person was 165 centimeters and somebody else was 170 centimeters, you could say that second person was 5 centimeters bigger than the first person. The first rule of statistics that I suggest is never use a number if you don't know where it's been. Typically, measurement is very, very difficult, and unless it's done well, the data that we work with or the numbers that we work with may not be that useful. School league tables I cited as an example of the difference between validity and reliability when it comes to the quality of the measurements we make. If something has high validity, that means it measures what we want it to measure. If something has high reliability, that means that when we try to measure similar examples of something, we get consistently the same results. School league tables are a good example of a measure that's very reliable. The information on which it's based is possible to measure very accurately and consistently. It's just based on the exam performance of pupils. And so similar schools will get exactly the same score. However, it's not a very valid measure in that pupil exam performance isn't necessarily a very good guide to how good or bad a school is. So they're highly reliable measures, but they're not very valid measures. Which one of the following is an example of a constant? Let's get the details of the question up. The speed of light in a vacuum, so far as we know, is constant throughout the entire universe. It doesn't change. The sex of a person sampled in a survey, clearly that the person's sex doesn't change, but different people in the survey will have different sexes, so it's an example of a variable. The same goes for the proportion of male children born each week in the UK. It'll fluctuate up and down. It won't always be exactly the same. It's a variable. A baby's weight at birth, Any individual baby obviously only has one weight, but different babies will have different weights. It's a variable. The number of legs of adults in Edinburgh, that's a variable too. Most people will have 2 legs, but some people only have 1 or maybe no legs. And so, unlike the speed of light in a vacuum, it's a variable rather than a constant. An example of an object or event that we measure in some way is a case or an observation. It's one of the collection of things that we collect information about when we gather data. The characteristic, property, or feature of a set of events or objects that we want to measure is a variable. We might have a group of people and we're interested in their income or their height or whether they have a particular medical condition or whatever else it might be. The result of an individual measurement of a characteristic for an individual event or object is its value. If we're measuring the sex of people, the values would be male and female. If we're measuring their income, it might be their income in pounds per month or something of that nature. If we're looking at chemicals, we might be interested in whether at room temperature they take the form of a solid, a liquid, or a gas. Yeah? A table that shows the number of observations taking each value for a variable is a frequency table. It just shows the frequency with which the cases take each of the possible values. So in the statistical literacy class, there might be 100 students, 47 of them are men, 53 of them are women. The frequency table would show opposite the value female, the number 53, and opposite the value male, the number 47. The name for a distribution where most cases take a value near the average and there are progressively fewer cases for values further above and below the average is a normal distribution. It's a distribution that occurs many times in social and natural phenomena. It's also a distribution that has lots of very valuable and interesting properties that we'll come back to again and again. The study that recorded babies' weights and whether their main carer smoked was the Millennium Cohort Study, a study of a group of about 16,000 babies born in the year 2000. If there's no association between 2 variables, we can say that they are independent of each other. Knowing the value of one of those variables will tell us absolutely nothing about the possible value of the other one. In statistics, a model, let's just see what options I gave you. Well, it's not a good looking statistician for a start. It's a simplified summary description of the real world. It contains what we think are the essential aspects and strips away everything else to keep it as simple as possible. A group of cases that we examine is just a data set. A model is more than a variable. It usually describes relationships between variables or particular aspects of a variable, and it's also more than just individual values. We typically use samples to measure aspects of the natural or social world simply because most of the things that we want to measure and examine are too big to measure and examine, or too costly to measure and examine, or perhaps measuring and examining them will destroy them. If you're testing materials, for example, to see whether they have the characteristics that they're supposed to have when they emerge from some production process, it may well be that in testing them, you destroy or alter them in some way. We can't test and destroy everything, so we just take samples. A system governed by the rules of probability is said to be stochastic. That's just a fancy name for, if you like, having random elements or having elements that aren't purely determined or capable of perfect description. When something's governed by the rules of probability and is stochastic, the knowledge that we have of it is to some extent uncertain. We can make estimates of its characteristics, but those estimates will only be accurate within certain limits. Probability is fundamental to statistics. In many different ways. It's important because, and most of the rest of the course is in some ways about exploring the different dimensions and ramifications of probability. But amongst other things, it allows us to make statements about the future. All statements about the future are uncertain. We cannot know definitely how the future is going to pan out. It allows us to estimate the amount of error in our measurements. If our measurements are estimates, we need to know how good or bad these estimates are likely to be, and probability allows us to do that. It also plays an essential role in random sampling, and as we'll see, random sampling is the basis of almost all measurement in the modern world, and random sampling depends upon being able to know the probability that any individual member of the population will be included in our random sample or not. So there are all ways in which probability is fundamental to statistics. If an event is random, that just means that we cannot predict it with certainty. It may occur or it may not occur. A good example that we'll use many times is tossing a coin. We know that it will come up heads or tails, but unless we're very expert at tossing it, we won't know which. In an experiment, the values of the experimental variable are manipulated. The typical form that an experiment takes is to control everything so that only one thing varies, and that's the experimental variable. If, with just varying that one thing, you find different results according to whether or not that thing was varied, you can be absolutely sure that it was the variation of that thing that caused the difference in results. It gives us evidence of a causal process. So that, for example, in a medical experiment, usually you will have people who are given some kind of treatment, maybe the administration of a drug, and a control group who don't receive the treatment, who receive a placebo. If the results for the experimental group are different from the control group, for example, they recover from the medical condition that they have rather faster, or whatever it might be, then we've got evidence that it was the treatment, it was the manipulation of the experimental variable that caused that difference. Sources of error. Even though we take a random sample, we have no guarantee that its characteristics will exactly match that of the population as a whole, had we been able to measure that population. By the way, when I use the word population, that doesn't just refer to people, it can refer to objects or anything that we want to measure. We can only measure the present. Usually we want to know about the future. If we are thinking in policy terms, collecting information about something so that we can change it or reform it or influence its future development, we nevertheless don't know how the future is going to pan out. We can make predictions about it, and sometimes these predictions can be extremely accurate, but they're nevertheless probabilistic. Our measurements may be unreliable, or our measurements may have poor validity. Measurement, as we'll see in the course, is typically a very difficult process. It's not about holding a kind of metaphorical ruler up to reality and reading off the results. Very often the things that we want to measure are intangible. You'll see a lot of surveys in the newspapers about well-being or happiness and so on. Just have a think about, how do you measure that? It's a if I get asked if I'm happy or sad, would I really know the answer? Um, if we look back in our lives, we can think of times which may not have been enjoyable at the time, but now give us some sense of satisfaction or achievement or reward. Um, Even if we're measuring more tangible things, um, a survey might ask about somebody's income. Um, if I asked you, what was your income last year? Would you know? What might be included in income? If I asked you, how much time did you spend studying last week? That question has an absolutely definite answer. You must have spent a specific amount of time studying, given that we can define studying in a particular way. But there's no particular reason why you should have any idea beyond a rather vague one of what that amount of time actually was. The Salk vaccine trial was a trial of vaccine for the polio virus. Wysiati, what you see is all there is. Daniel Kahneman's statement about the way in which we typically process evidence. And Daniel Kahneman is the guy who argues that cognitive illusions are similar to visual illusions. The way our brains work encourage us to treat evidence in a particular kind of way. And one way of thinking about statistics is as a set of procedures that systematically combats the kind of cognitive illusions and distortions that we as human beings tend to be prey to.